A very good day to all. Welcome to the second class of Chapter 3 on the simulation of reactive processes. During the last class, we have gone through the balance-based model, especially on the R-stoid, when the reaction conversion and also the extent of reaction is given. So in this class, we will be focusing on the kinetic-based model, and in particular RCSTR and also RPFR. So let's shift to the PowerPoint. Under the kinetic-based model of X1 Plus, other than RCSCR and RPlug, we have also RBatch. But the principle of using the kinetic-based model is the same. So in the future, if you have the chance or if you have the need to use RBatch, you can adopt the knowledge that you have learned in RCSCR and RPlug and use it on your own, right? So in kinetic-based model, reaction kinetics, of course, is taken into account and it must be specified. This model can be specified in terms of power law and also Langmuir, Hinshelwood, Huygens, Watson if you are using the built-in models. But if you want to include your own kinetic equation with special format, you can actually use the user subroutine function. So a catalyst for a reaction can have the reaction coefficient of 0, meaning in this case, even though you are using the catalyst does not involve in the chemical equation. You only use the catalyst to expedite the reaction and to increase the rate of reaction. In order to include the reaction into the kinetic-based model, we normally use reaction ID in X1 Plus to include the required information. So there's some basic reaction kinetics knowledge that you have to revisit. So the first one is the definition for reaction kinetics. From reaction kinetics, you will get to know what is the reaction mechanism and also the rate of reaction. For example, we have 2A plus 3B producing C plus 2D. So in this case, for the forward reaction, we are asked to assume that the reaction is second order in A. And based on this information, we have written the rate equation here. Rf is equal to Kca squared. Typically, concentration is used in the rate equation. Unless you are having a vapor phase reaction, then we can use the rate law in terms of partial pressure. So from here, we are asked to specify the coefficient, which is the stoichiometric coefficient, -2 and -3 for A and B respectively. Negative means they are reactant. C and D, they are having the stoichiometric coefficient of 1 and 2 respectively. So in terms of exponent, it is actually referring to the order of reaction. So as mentioned earlier, it is second order in A. So therefore, 2 is given to A, component A, while the others are given 0. Right? So the same thing is going to reverse reaction. The same principle is applicable to reverse reaction. Just use the same to write the stoichiometric coefficient and also the exponents for the reverse reaction. So for the rate constant, we can express it in terms of temperature using the Arrhenius equation in the second equation, as in the second equation. But if T0 is specified, the second equation can be further reduced to the third equation here. And if you want to simplify further, when n is equal to 0, then the third equation is further reduced to the normal Arrhenius equation that you learn in CRE. K is equal to A times the exponential of minus E over RT. So A here is the pre-exponential factor, E is the activation energy. So let's compare the normal Arrhenius equation that you learn with the kinetic information that you have to include into exponent plus. Comparing the equation, K in the typical Arrhenius equation is actually the kinetic factor in exponent plus, while A, the pre-exponential factor in the normal Arrhenius equation, is actually the K in the exponent plus kinetic equation. So a summary is given to you, so you have to process the kinetic data accordingly before you include to exponent plus to ensure what you include is correct. So other than the rate equation, you have to measure the performance of the reaction using conversion, selectivity, and also yield. And these are the equation for you to quantify the X, S, and also Y accordingly. F here is the molar flow rate. A is denoting the reactant. A naught means the naught here, 0 here is the initial condition. Right. P is the product. So for RCSTR, as I mentioned, you can use it when the rate equation or the kinetic information is given. It allows any number of feet, and it allows more than or up to 3 products. You can have vapor, liquid 1, liquid 2, or vapor, liquid, and also free water. So the duty can be calculated to you if the temperature is given, or vice versa. This RCSTR can model equilibrium reaction concurrently with the rate-based reaction, meaning you can have more than one reaction. Some of the reaction can be in equilibrium, some of the reaction is rate-based equation. So let's start example or exercise 3.3. So the details of this exercise is given in the PDF file of RX003. We have this reaction, cis-2-butene isomerized to trans-2-butene. So this is a chemical equation. So it is an irreversible liquid phase reaction with first order in the reactant. So based on this information, the rate law is written here. RA is equal to KCA. So we are asked to determine the residence time to achieve the conversion of 90% in a CSTR. The assumption that we have to make is it is at steady state and the homogeneous reaction, and we are asked to use the NRTL as the property method. So from the analytical solution, meaning if you solve this manually, you can get the answer for the residence time required to achieve the conversion of 90% is 39.13 minutes. Verify the manual calculation using the simulation result from exponent plus. So your task now is to perform the simulation using exponent plus and verify this number. So this one I will leave it to you. The approach used is actually the same with the one you learned in CRE 1. It is just the more balanced equation for CSCR here. Instead of V naught, they have actually used Q as the volumetric flow rate. So you can change Q to V naught if you are not familiar to. But everything is the same. Just combine the more balanced equation, stoichiometry, and also rate law. Then you can calculate the residence time accordingly. So it's not so difficult because for CSTR, only algebraic equation is involved. You can solve it easily using a manual calculation. So let's analyze the problem. Yeah, CSDR, of course, we have to use RCSDR for the simulation. The number of feet, only one, with the condition of 10 bar, 25 degrees C at 1 kilomole per hour. And the reactor is at the same temperature and pressure with the feed. And remember, the reaction is in liquid phase. We have to set the valid phase as you have to set the reaction as liquid phase. Later on you can choose accordingly. And the residence time, to start with, you can set as 5 minutes. The rate law here, as given just now, is KCA is a first order reaction with the K value of 0.23 per minute at 25 degrees C, okay, at certain temperature. So let's solve the problem. You have to create a blank simulation, list the component, list or select the property method, and generate the properties before you save the file in backup format. Then you construct the flow sheet. So of course, RCSCR should be chosen, and connect the block with the stream and name the block accordingly using the correct convention R101. Next is for you to put in the feed specification, temperature, pressure, and also the flow rate accordingly. And next is the space for you to include the block information like pressure and temperature. The valid phase here, I have actually put it vapor liquid, just in case you have vapor in the reaction. Of course, the reaction happened in liquid phase, but we can put vapor liquid. And another specification, I have chosen residence time because we have to specify the residence time. Just to start, you just put as 5 minutes. So if you click next, you'll be guided to this page. Just click new. You'll be given the name for the first set of reaction as R1. Just use the default name. And after that, you are asked to choose the type of reaction or reactor model, kinetic model. So this is the type of kinetic model. So you just need to choose general before you opt for power law or Landmeyer-Hinsel later on. So remember, this is a very important step. You have to choose general. So once this is done, then click next. You'll be guided to a section for you to include the reaction details. So under configuration, you have to put the chemical equation. You have reactant and products with the stoichiometric coefficient of 1 each. Of course, negative here is denoting the reactant. So next is the space for you to put in the kinetic. Remember, it is a liquid phase reaction. Then because the rate equation is given in terms of concentration basis, so you have to choose molarity here. And the unit for the rate is kilomole per meter cube per second as given in the question. Because the unit for the rate is in second basis, we have to change the rate constant given just now. Instead of 0.23 per minute, we have to use 0.003833 per second. It's just because of it should be in second basis. Please, this is very important to avoid the mistake or error of the simulation. So activation energy here we put 0 because the rate constant given is at certain temperature, which is at 25 degrees C. So E is 0 here, we have to set 0. So once you have done this, click driving force. Driving force is basically for you to include the order of reaction. So it's first order in cis-butene. Just put first order in cis-butene. So the others you don't need to disturb. Okay, just put the order of reaction here and close it. So once this is done, just click next. You'll be guided to run the simulation and check the result. So let's have a quick check on the stream results under the block. So this is under R101, stream results. So the conversion over here obviously is not 0.9, which is 90%. If you calculate it accordingly based on the molar flow rate of the reactant and also based on the molar flow rate of the reactant, then the conversion is only 53.5%, which is 0.535, meaning the residence time for 5 minutes is not sufficient for us to achieve the conversion of 0.9. So what should we do next? Before we do the next step, let's have a 5 minutes break and we'll continue to use a new function here, the design spec. Okay. Thank you.